Hello, welcome to Algebra 2. We're in Chapter 7. We're section, what I like to call section graph here. I'm trying to finish up all the graphing that's been going on during the first four sections, and I think if you look back at each of the four sections of Chapter 7 in the textbook, I don't really recommend that you do, but if you did, you would find that they all have some level of graphing in them. One last thing on the standard that's not directly addressed in the textbook is making sure you're finding the intercepts of all the graphs. I take that to mean both the x-intercept and the y-intercept for both exponential and logarithm graphs. If you remember well, you'll know that we kind of found one intercept for one kind and one intercept for the other kind, but today we're just going to nail it down and make sure we're doing both kinds of intercepts for both kinds. But to be able to actually calculate that, given the limitations of our calculators, you're going to need to learn this thing called the change of base formula first. We had to get around to it anyway. It's as good a time as any. We're not going to use it too much today, but it's going to pop up every once and again. So the deal is this. Your calculator doesn't do various bases that you want. If you have a TI-84 that's relatively recent, it does, but all other calculators that students tend to use don't. So you had to use this formula, which basically says you can change the base to whatever base you want as long as you divide by the old base's log. It takes an example to look at it. So if you look at the bottom here on example 1, you see that we're trying to do log base 5 of 100, and you have two options. You could do it with the log button on your calculator, because that's base 10, or you could do it with the natural log, or the ln, or as I like to jokingly say, the ln button on your calculator. The trick is to make sure that whichever one you're using, you have to divide by that new log of 5, because that was the old base. It makes more sense looking at it than me talking about it. So pay attention to what happened in example 1. It's going to come up in our graphing situations. So to do the graphing, I really recommend that you go ahead and you pause me, because otherwise I'm just going to talk. You pause me and you look through example 2 and example 3. They're both excellent, I know, because I made them. And I'll wait a few seconds for you to go ahead and pause, and then when you come back, I'll still be here, and we'll be able to do this one together. Welcome back. All right, so to finish these notes, I got a couple examples I just want to work through with you. Reading the set out examples that you already have, I think, has a lot of value, but also watching them happen has value. So I did a couple for you. I've got a couple here to watch happen. In this first one, we're meant to graph y equals e to the negative 1.5x minus 1. Good times. The first thing you'll probably notice is that it's an exponential function, but it's base e with a negative coefficient, so that makes it an exponential decay function. Remember, when the bases change, if it's less than 1, it's decay. If it's more than 1, it's growth. But when you're talking about base e, you got to look at the exponent situation. And that's a little different than the other ones, but we talked about that in the last set of notes also. Now, this is an exponential decay function, and it went ahead and it got shifted down 1. You want to make sure that you notice that. And so that takes the asymptote down to y equals negative 1. Remember, exponential functions, growth or decay, they have horizontal asymptotes, and so those get adjusted by vertical shifts. This one went down 1, got yourself a horizontal asymptote at negative 1. Okay, now we're going to go after both intercepts. First, the x-intercept. To do the x-intercept, you got to make y equal to 0. That's the whole point of an intercept. It's where the other variable equals 0. All right, so go ahead and rewrite the equation with 0 in instead of y. There you go. The 1 isn't really causing any problems, so let's move it out of the way. 1 equals e to the negative 1.5x. Now we have to deal with the fact that x is up in the exponent. The key, as always, to getting things out of the exponent, changing it to logarithm form. So log base e of 1 equals negative 1.5x. Remember, when you shift forms, the little pieces in the equation seem to flip-flop around a little bit. That takes such a long time to get used to. But here we have log base e of 1 equals negative 1.5x. Good times. You might already know kind of what's going to happen at the end here because of the specific numbers here, but I'm going to pretend you don't, just to show you the process in case the numbers end up uglier. Anyway. All right, so we've got to divide by negative 1.5. So it's log base e of 1 divided by negative 1.5. Boom. Now, that's great, except we don't have a log base e button on our calculator. Oh, wait. Yeah, we do. It's ln. So it's ln 1 divided by negative 1.5. And if you just throw that into your calculator, you want to make sure that you close the parentheses after the 1. If you're doing that all at once on your calculator, you get 0 is the answer. So the x-intercept is 0, 0. Good times. Now, moving forward, you might already know the y-intercept, given the specifics here, but I'm going to pretend that we don't. We're just going to go through the process. All right, so to get the y-intercept, you make x equal to 0. This is something that should be fully boring by now. So rewriting it where x equals 0, y equals e to the negative 1.5 times 0 minus 1. Boom, you work your way through. In the exponent, negative 1.5 times 0 is 0. So the exponent's now 0 overall. E to the 0 is 1, because anything to the 0 is 1, except for 0, but we don't speak of that. And then, so 1 minus 1 is 0. Our y-intercept is 0, 0. You might very well roll your eyes here, because you could say, of course it was. But here we are. It's 0, 0. Go ahead and plot, I guess, that intercept, both of those intercepts. Depends on how glib you want to be as you talk about it. But put the dot down. And then swoop our way down. Remember, it's exponential decay, so that's our shape in general there. If you want to get specific about other dots, you're welcome to make a t-chart also. Probably will drive you crazy. So I recommend you move away from that if you can. But, you know, if you're forgetting shape, you always could do it as some sort of backup method. All right, we've got ourselves a graph. It's an exponential function. The domain is all reals. Remember, any exponential function, growth or decay, the domain is all reals. And in this case, the range is all the numbers above negative 1. It's because the asymptote was at negative 1. That's it for this first one. Now that's a lot of work, no doubt. But you got to go through each of the pieces here. And let's go ahead and look at the next one. Now this is a logarithm graph instead. I didn't point out that it's a logarithm graph because it says log in it already. But it's a logarithm graph that's moved left 1 and down 2. Now the key to remember is that for logarithm graphs, the horizontal shift is the thing that matters. Particularly because logarithm graphs have vertical asymptotes and they get changed with horizontal shifts. So this one, boom, was a vertical asymptote on the y-axis, but it got shifted left 1, so it's x equals negative 1. Got yourself an asymptote. Now we'll go ahead and go after the intercepts. Here, intercepty? No, okay, I don't know. Okay, so x-intercept, you make y equal to 0. Go ahead and put 0 for y, rewrite the equation. All right, that minus 2 on the end can move pretty easily. Adding 2 to each side. And now we're stuck because x is inside the logarithm. I've said it before, there isn't a whole lot of different way of saying it. If your variable, the thing you want, is inside the logarithm, the way to get it out, to get it free, is to change the format. So change it to exponential form. 3 to the 2 equals x plus 1. Like I said before, when you switch between logarithm and exponential forms, or exponential forms and logarithms, either way, the order of the things in the equation kind of shifts around wibbly-wobbly, but that's the joy of math's pure beauty, I suppose. All right, so you got 3 squared equals x plus 1. 3 squared is 9. That's not too exciting, hopefully. And then if you move the 1, you got yourself 8. So the x-intercept is at 8, 0. Boom. All right, now moving forward, we can go ahead and get ourselves ready for the y-intercept. The y-intercept is when x is 0. So go ahead and rewrite the equation, but this time make x equal to 0. 0 plus 1 is 1, so boom. Now again, because I was trying to make this a little bit more palatable, and also because it was late at night when I made it, log base 3 of 1 is actually a really nice number. You might immediately know what it's going on, but let's pretend we don't. I'm going to use this as an opportunity to remind us of the change of base formula. So I'm changing it to log 1 over log 3. If you're paying super duper close attention, you'll notice I changed it to common log. Doesn't matter. It could have been natural log 1 over natural log 3, or as I like to say, ln 1 over ln 3. I personally prefer natural log. I have never met an Algebra 2 student who prefers natural log, so I suspect you don't. That's fine. Not a big deal. Either way, the base has changed, and because of that, you're ready to be able to put it into a calculator. Now, if you do that, remembering to close the parentheses correctly, you got log of 1, close parentheses, ka-chunk, divided by log of 3, close parentheses, ka-chunk, minus 2. You get 0 minus 2, which is, in fact, negative 2. So, our y-intercept is at 0 comma negative 2. Go ahead and dot both of those. It's not very exciting to put the dots down, but there they are. Knowing that it's a logarithm graph, we can go ahead and swoop our way up. Yahoo! And from there, start talking about domain and range. Now, logarithm graphs, the domain is all the numbers to the right of negative 1 here. All the numbers to the right of the asymptote. In this case, negative 1. And the range for all logarithms is all real numbers. It's been a lot of work here. I'm hoping that this helps us continue to get practice on exponential and logarithm graphs, especially now that we have them mixed around. Also, in here somewhere is the issue about changing or noticing what's going on between exponential growth and decay. Also, continuing to notice to not freak out whenever you see an e or a natural log in a problem. And all of those things I just said, those are all review. Additionally now, we're talking about doing both intercepts for each graph. Sometimes the intercept won't exist, or one of the intercepts won't exist. That happened in example 3, which is back one of the written out examples. It's important stuff. So please don't hesitate to let me know, which means please do let me know if you have any questions. This is not easy stuff, but I think we've taken it at a pace where you probably can begin to follow along. So I hope you enjoyed it. Let me know if you have questions, and thanks as always for watching.